Welcome to the 16th lecture of graph theory. So, in the last class we were looking at Vizing's theorem. So, this was the theorem, let G be a graph with maximum degree delta and then its chromatic index chi dash of G is in between delta and delta plus 1, that is either equal to the maximum degree or one more than it. So, depending on whether it is delta or delta plus 1, we call it a type 1 graph or a type 2 graph. So, now we were in the middle of the proof, so we will look at that once again. But before getting back to the proof, so we were the main concept in the proofs, both in the edge coloring and in the vertex coloring, up now what we have seen was essentially by considering just two colors, concentrate on two colors, and we will look at the, say in the case of vertex coloring, we will look at the vertices colored with these two colors, say maybe red and blue, red and green, and then we consider the subgraph formed by those vertices. So, we can see that because the entire graph is not colored red and blue, there are other colors also. So, naturally we will not get the entire graph. So, it may so happen that it may give us a connected component, some connected components, right, something like this may come, right. So, then with some structures, right. So, I will just draw like this may be the connected components. So, of course, this red will be connected to green, green will be connected to red. How they are connected is we do not know. So, maybe some structures. So, it may be there may be several such structures. So, with red and green, right. So, some connections in between. So, with red and green alone. So, all the other vertices, maybe if there is an yellow vertices, so it will be that yellow vertex will not come in any of this thing. So, it may be connected to this, but these are all outside vertices. So, now the observation that we were making use of was that here it does not matter, for instance, in this connected component of red and blue, red and green, if I change each green vertex into a red and red vertex into a green, so it will not affect the coloring, it will be still proper. For instance, I could make this red and this green, so interchanging the colors red and green in this component. Why does it affect? Because the other connected components of red and green vertices will not have any edge across this. So, therefore, this change will not affect them, because they, what do they care? They only want their neighborhood to be different from them. The neighboring vertices should be colored different from what color they got, right. So, therefore, they do not mind if we change the color of each red vertex to green here and green vertex to red here in this component. And who can the remaining vertices, for instance, if there is a brown vertex here, so this vertex may see that there is a color change in its neighborhood. For instance, if this was so the red change to green, but it does not matter to it because its color is brown, it is neither red nor blue, right, because therefore, in its neighborhood whether it sees red or green is unimportant to it. So, this change will not affect that also. Therefore, we can this connected within the connected components of red and blue, we can interchange the red and blue with each other. This was what we made use of in the last proof in the vertex coloring. So, like many times in the proof of Brooks theorem. So, we were studying the connected components formed by certain two colors, say green and red, and then containing a green neighbor of the vertex which we were considering as part of the induction. And then first we argued that the red neighbor also will be part of the same connected component where the green neighborhood comes, right. So, when you consider the red and green connected components, and then we argued that that has to be a path from this neighbor to the other neighbor. So, that was by rigorous analysis, but in general, so in that proof it worked out like that, but in general this in the vertex case of vertex coloring, if you look at a connected component formed by red and green vertices, that can be an arbitrary graph. You mean there is no reason to think that it should have this, it should be a path, or this should be a cycle, or it should be of a particular structure. It can be anything, right. So, therefore, so no more help available there, just that we can exchange colors there, but that itself is a good enough help that in many cases we can, making use of that opportunity, that possibility, we can manage coloring. But in the case of edge coloring, so we are, see, first of all we should notice that edge coloring is only a special case of vertex coloring, just that we are the edges, for instance, if you consider the line graph of the graph, what was the line graph? So, each edge of the graph becomes a vertex, and whenever two edges are adjacent, then they will make the corresponding vertices adjacent. So, that was the line graph, we have studied it earlier. So, therefore, it is very easy to see that the edge coloring of a graph corresponds to a vertex coloring of its line graph, the proper vertex coloring of its line graph. Therefore, edge coloring is only a special case of this the vertex coloring. So, whatever it is, but if it is edge coloring, so for instance, if you consider edge coloring, so you can see that the, if you consider the edges corresponding to two colors, say red and green, they will not see this connected components, connected subgraphs formed by them will not be very complicated, because for instance red and green. So, here this vertex, if you consider, there can be only one red edge and one green edge incident on it. So, it is not possible to have another here, because that will not be a proper edge coloring, or another red here or red here, or it is not possible. So, you can have one red here now. So, these are all wrong. So, this is not possible, this is not possible, right. So, therefore, we can have a red edge from here, and then we can have a green edge, that is all, because that will be after one red edge you will see only a one green edge. How will it stop? It can abruptly stop, like it can go with and stop, then say that I do not see any green edge anymore. So, it can be a path, or it can go back and maybe complete a cycle like this, that is also possible, right. This is also, these are the only two possible cases. So, you can see that this is completing a cycle, then it is red, green, red, green, red, green, an even number of edges are there in that such a cycle, or it can be just a simple path like yeah, red, green path. It starts and the maximal subgraphs will be like that, right, the connected subgraphs will be like that. So, therefore, in the bipartite graph proof, that when we proved that the edge chromatic index of a bipartite graph is delta. So, we used this property only. We pointed out that if you consider induction, if you did induction, so and we considered some edge and removed it, right, this was what we did, x, y, and then we showed that see the of case by induction we have an edge coloring in the remaining graph, and then so we identified a color which is missing at this point and identified a color which is missing at this point, and in fact if we get a missing color, the common missing color at x and y, then that edge color would have been okay for this edge, because then there was no conflict at x or y, right, we can give that common missing color here. So, if there is no common missing color, we just took a missing color of x and missing color of y, that means the missing color of y will be present at x. Say if green is missing here, then green will be present here, and then suppose red is missing here. So, the red we can keep a track of the green, red, and you know that it is a path, and we argued that if it is not coming up to y, so it cannot come up to y, because otherwise it will form an odd cycle. It is not there in the bipartite graph. On the other hand, if abruptly stops, it is just a path, then we can switch colors on this green and red, and then here red will come and this will become green, and therefore, the green will be missing here, and then here also green is missing. So, that green color will be available for this thing. This was the argument for bipartite case. Now, coming back to the Vizing's theorem, we want to do the same kind of trick. So, but this is a little more complicated here, basically because this is not bipartite graph, and the argument that fails is that see, when you consider an edge x y like earlier and you remove it, you consider by induction edge coloring which uses only delta plus 1 colors for the remaining graph, and then if you consider a missing color here with respect to whichever coloring we consider. So, there will be missing colors because delta plus 1 colors are available, and then now the degree has gone down to delta minus 1 here. So, 2 missing colors will be there. Any of the missing colors, say green is red is a missing color here. So, and then green is a missing color here. So, common missing colors are not present, because if common missing colors are there at x and y, then naturally that missing color is enough. We can give that color to x y, because there will not be any conflict either at x or at y. Therefore, we can assume that the missing color at y will be present at x, and then the missing color at x will be present at y. Maybe red is missing at x, so then green is missing at y, this will be there. And then if I keep track of the red green missing color, somehow if you could argue that this will abruptly stop somewhere like this, so and then go somewhere and stop, so go somewhere and stop, then we could have exchanged the colors red and green in this path, and then that would have been enough, because here red will come, here red will come, and this will become green and so on, and then that will release the this will become that will release the green color, and green color would be possible. I mean, for this edge we can use green color to color the xy edge. This could have been possible, but then unlike in the bipartite case, we cannot argue that this path cannot reach y. It can reach y. In fact, if we want to argue that okay, indeed, suppose for contradiction we assume that we cannot extend the delta plus 1 coloring of this underlying. So, the by induction whichever coloring we got for g minus e cannot be extended to g, then it means that whichever this using this missing colors, whichever path we create, it has to if it's it starts from x and it should reach at y, right. That is why when we try to exchange colors, the missing color the one color appears here, but then the missing color becomes different, but then now y also loses its missing color, and the original missing, in fact the missing colors change their role. I mean, from x to y they move, that is all, right, because the green was missing at y, then green will be missing at x now, and red will be missing at y now, because this will become green after recoloring, right. So, therefore, that will not help us here. So, but one preliminary observation that we make is that if you, for induction's sake, if you remove one edge and consider any coloring of the smaller graph, it should have this property. If you start from x with a color that is missing at y and then follow with its missing color at x and so on, that path has to go and end at y with, of course, the color which was missing at x, right. That is a must. This is what we noticed in the last class, first thing, and this is the first observation for the proof. Now, we set up this induction this way. So, we picked up a edge, picked up a vertex, right, and then so we looked at its neighbors, maybe these are the neighbors of that vertex. So, we can call it x, and these neighbors, one of them can be called y0, because we are going to number them in a particular order. So, the first thing is to remove this edge, y0 edge. So, maybe I can put it as, when I remove that edge, I can put it as, see, this is removed, right. So, when you removed, so now it is g minus xy0, right. So, this one does have a coloring using delta plus 1 colors. Okay, the question is, can we extend that coloring to the g? That means, can I somehow find a color for xy0 also from the used delta plus 1 colors, from the used colors, right. Of course, we will look at the edges, the colors that are used on the edges of x, edges incident on x, and we suppose we find out a missing color here, right, and we look at the neighborhood of y and we find out a missing color here. Suppose they were common, there was the missing color at y0 was the same as the missing color at x, then that missing color would have been enough for coloring this edge, right. But then that we can infer that the color that is missing at x, say, suppose I will say that this color, so this violet color is missing at this color is missing at x. So, that means none of the edges at incident on x is violet, right. And now what I say is, so this color, violet color, is missing at x. Now, you can say that violet color is present at y0, right. Violet color is present at, but whatever it is, it's clear that with respect to this coloring C0, why? Because the C0 is the coloring which by induction we picked up for this graph. This will be called G0. This graph by xy0 is deleted, and now what I'm going to do is to search for an edge among these things. For instance, this y0, at this y0 there is one missing color, right. Maybe at least one missing color is there, in fact 2 are there. So, let us say this is a red color missing, red is missing here, red is missing here, oh, red is missing here, okay, red is missing here. So, suppose red is missing here. If red is missing here, and then what happens is, so you know that if red is missing here, red cannot be missing at x. So, a red edge should be there somewhere here, right, among these. But so, we will pick up the red colored edge, and then let us say we will move this to here, in fact. So, in other words, I will rearrange the neighbors in such a way that, so this is x, right. So, here we have the y0, and missing is red is missing here. Now, I will pick up the red colored edge here, and then I will call it y1. You remember this was this edge was essentially not there. Yeah, this edge was like this. So, it was not present in G0, but you see this is a red colored edge, this is a red colored edge, and this is red is missing here. Now, we look at what is missing here, maybe green is missing here, green is missing here. Now, because green is missing here, so there should be some edge here among the x which is green. So, there should be some edge which is colored green, right. So, let us say this is green colored. I will pick up that edge and then bring it here. Why should it be there? Because if green is missing here and then green cannot be missing at x, it should be present at x. So, there should be at least one edge. So, then I will bring that green edge here and call it y1, and then we will see what is missing here. Maybe yellow is missing here, yellow is missing here, right, and this is, sorry, y2, and then we will search for the yellow colored edge here. So, there should be an yellow colored edge. So, yellow colored edge if I get here, then I will bring it here and make it y3, and then I will look for the brown colored, right, but maybe brown is missing here, then I look for the brown. So, I keep doing it until I can keep going. When do I get stuck? See see, as I take more and more edges, so the remaining edges will finish off, and it may so happen that the missing color, it has to be present among the edges of x, but it may be already taken. It is possible that here the next time I may see that the red color is missing here, say y4, red color is missing here, but red color is already taken, right. So, we cannot take it again and put it back here. In fact, this cannot be moved to here, this has already got a position. So, we will stop there if such a situation comes. If the missing color at this point is such that is already taken, then we will stop there. So, the situation now is like this. So, now what we have done is we picked up this vertex x, and then we, of course, this was the edge in G0, when we removed we got G0, this is Y0, and based on this only we got the coloring, that is C0, the base coloring of with which we are starting. Then we are arranging the neighborhood of x, not necessarily all the neighbors, but as big a sequence as possible like this. So, for instance, this is Y1, this is Y2, this is Y3 until some yk, and then there can be other edges, but we are not bothered about that, right. We will play with these yk vertices. But what is the property of these yk neighbors? So, the color with respect to C0, what is missing here? So, say for instance, if it is red is missing here, then this is, say red is missing here, then this is red colored, right. If suppose now green is missing here, so green is missing here, so now this is green colored, right. Suppose brown is missing here, then this is brown colored, like that. So, this is the way we have selected it. What color is missing at yi will be the color of the xy edge. This is the way we have it. And what happens at yk? Yk, it's that the missing color here is already among these. So, somewhere here the missing color of yk here is present somewhere here, that is why we could not take another y, because see it's the missing color should be present at x, because otherwise what we can do, see the otherwise what we can do is, say we will move we will put back this edge xy0 and then give the color red to xy0, because anyway here it was missing, and then x won't mind because anyway x was already seeing a red. If you move it to here, it's okay, and here this will be colored with this color. In fact, the green will move here because y1 will not find any problem because it was missing here, and say x will also will not find any problem because anyway just moving colors here, right, rotating colors, like, and then this will be moved in some kind of, we will rotate with respect to this x, we will be rotating colors towards xy0. So, because xy0 didn't have any color before, so that xy0 will get the color of xy1, and xy1 will get the color of xy2, and xy2 will get the color of xy3, and so on, right. Therefore, what happens is xyk will become empty, colorless, and then it will, if it so happens that the missing color here is missing at x also, we could have given that color to there. Therefore, it should, if we cannot do this thing and get a coloring for G, it means that that will never happen, right, because the color should be there at x, but then just that it is not in the remaining edges, it is just that we have already seen that color somewhere. So, we will not be able to the color the xyk edge with that. That is why it happens. So, the trick here is a kind of rotation. For instance, in any of this y0, y1, y2, yk, see you, so the what you can say is you can empty, say xyi edge So, in other words, we can derive a coloring from the base coloring of C0, say for by rotating. Once if you rotate, you will get the coloring C1, that means the XY1 color will go to XY0 and this will become empty. C2 is obtained by rotating 2 times, this will go here and this will go here and this will become empty, that means colorless. Similarly, CK is a coloring obtained by rotating it k times, that means y1 goes to y0, xy1 goes to xy0 and xy2's color goes to xy1 and so on. Xyk's color goes to xyk, yk minus 1 and xyk. This is some kind of derived coloring but rotating. The good thing about these colorings C0, C1, C2, Ck, they are the colorings of very related graphs. Essentially, we will see some kind of way of deriving this ith coloring from the base C0 coloring by some rotations, right, I rotations we can get it back. So, they are all the colorings of very close graphs, just that one edge is missing, but very the edges that are missing are we understand which edges are missing and then we know how to convert a particular coloring to the other coloring and all by this rotation strategy. This is going to help us, right. Now, the final step for all these things are only a setup. Now, how will you prove it? Now, the point is I will look at yk and then there is a missing color at yk and there is definitely a missing color at x0. So, we already told that let it be violet color is missing here, it is missing right here. So, what about violet in yk? So, yk violet should be there, because as I told, because if I had considered coloring Ck by rotating and emptying the Cyk, if violet is missing at Yk also, then violet color would have been appropriate for that, right. We will rotate it and create my Ck where all the other edges xy0, xy1 all of them are colored, but just xyk is not colored. There I would have given the violet color to it, right, is not it. So, therefore, so it is if violet color is missing at x, then violet color should be present here, but then I can start. So, there is some color which is missing at here, say let us say the green color was missing at here, suppose green was missing here, green was missing here, then I can start a violet green path here, right. Where should it reach? So, because the this green color is missing here and violet color is missing here, as I told before, this should go and enter x, reach x somehow, this path violet green path should somehow reach x when in Ck when I consider the Ck, when I have rotated all the colors and now the empty edge is this only, right. So, I should somehow enter it. We know that the violet color is not among these, because in that case this would not have been the last in the sequence. I would have put that violet colored edge also after this, right. So, violet color is somewhere here. So, sorry, not violet color, green color is somewhere here, namely say this is the green colored edge, right. So, somehow the only way to enter this system and reach x is to go through this green edge. That is the only way, because violet is anyway not there, the violet green path has to enter through a green edge. So, it will somehow reach you see, because is a y2 was this thing. So, when I created, I have rotated all these things. Now, where will, so y2 had this color. So, let us say I will draw it once again. So, this is x, this is my y0, y1. So, here is the yk, and now I have rotated the colors. So, and then therefore, see, initially green color was here. So, but by rotation this is gone here, right. So, because essentially this was the green was missing here, so that is why the green is available here. So, by rotating, then this took the place, then here of course here we have you can see that here we have the dotted edge now. Here we have the dotted edge, that means missing edge. Now we trace the violet green path in this, and definitely it has to reach here by a violet green path, right. Somehow it should reach here and it should enter through this thing. So this is this entire sequence violet green is outside this system of spokes here, because here this x and its neighborhood, right, this edges incident on this is not participating in this part, and the only place it participates is this. Once it participates, it reaches x, right. So therefore, so when I start the violet green path from yk, it should reach y1. For instance, if I had started the violet green path from y1, it should reach here also, right, because it is totally outside, and if after deleting this thing. Now what we do is consider again the original coloring. So this is x, right. So now our this is the original coloring. I am going back to the situation where this is the missing color. So this is the missing, so this is y0, that is my base coloring of case c0. So this is yk, right. So now you see the green color was here, right. Now green is missing here, that is why green color was there. Now if I considered when I consider the violet which is present here, violet green path from here, you know, it is reaching here, right, violet. We have already seen that it will enter through a violet green path here. It's reaching here, but then the green edge is now here because we rotated back, right, by one step. Now the trick is to rotate up to here. For instance, we will consider this one, so we will rotate here. Suppose this is yi, this is yi plus 1. So up to I we will rotate. So up to here we will rotate. So these things are intact, we won't change them. See, we will consider the color Ci, right. So that means this will become empty. This will become empty. So this will become empty. Yeah, this will become empty, and yeah, so this will become this will be as such, you know, this is the green color here. For instance, this is the green color here, this will become empty. Now we know this is green is missing here also, like green was missing here, green is missing here also, and violet is missing here. Therefore violet should be missing here, violet should be present here. Okay, we know that violet is present here, and then this violet green path, if I trace, what should happen? We know by our earlier argument, this violet green path should enter x somehow, but then if we trace the violet green path, we know that it has to reach here all the way to yk, right. There is no other way, because we have already seen that there is a violet green connection from yk to yi, and there is only one such connection, it will reach here. But we know that there is no green edge here to enter here, this edge was not green, right, isn't it? The green was missing here, isn't it? So therefore we will not be able to enter here, green was not. So this is a contradiction. This is a contradiction to the fact that violet green path should reach x somehow. So this is the this is a contradiction, and then therefore we assume that we will be able to the swap colors here now, violet and green, and then make violet available for violet will be missing in y also as well as x. So therefore violet will be we can give violet to xy edge. This is the proof. So therefore we see that this can be colored in delta plus 1 colored. Induction completes. This is so what we have now done is the proof that any graph G can be colored using edge colored using at most delta plus 1 colors. So we will leave edge coloring here, and then now we will look at some other topics related to coloring. Like for instance, when it comes to coloring, maybe one of the most important graph class, special class of graph is planar graphs. Why is it? Because the most famous problem in graph coloring theory, probably in graph theory itself, is the 4 color problem. So, it asks about the chromatic number of a planar graph. What is the chromatic number of a planar graph? So, the conjecture was that the planar graphs can be colored using at most 4 colors. So, this conjecture was started in the 1800s. So, when Francis Guthrie wanted to the color the map, the countries, the map, the world map with just 4 colors, such that the neighboring countries get different colors. You can easily see that this will convert to if for instance each country is considered a vertex, and if we draw a graph such that 2 vertices are connected when the corresponding countries are countries corresponding to those 2 vertices are neighboring countries, then we will get a planar graph. It is not very difficult to try that out and figure out that it is a planar graph. So, therefore, this problem of, so he asked whether any map can be colored with at most 4 colors, only 4 colors. So, this became the famous 4 color problem, and then it took so many years, almost a century to come up with the proof. So, we are anyway. So, we will not do a proof of 4 color theorem here, it becomes quite complicated and long. So, it's what we are going to do is to see how it can be vertex colored using 6 colors, 5 colors, etc. 4 color we will leave out because it is not possible to do it in a class. So, let us explain what are planar graphs first initially. So, the graph drawn on the plane in such a way that no 2 edges intersect other than at the end points is called a plane graph, right. So, we can say this is right if I am drawing a graph like this. So, now so you can see that the graph is drawn such that if you take 2 edges, they do not intersect at all other than at the end points. Okay, the end points is intersecting. So, maybe you can draw like this. So, these are like that, but then when I draw like this, then this edge is intersecting this edge here, right. See, so therefore, this is not a plane graph, right. So, the planar graphs are those graphs which can be drawn on the plane as a plane graph. That means without the edges intersecting each other, crossing each other. For example, if you take this graph, so this is not a plane graph. So, drawing because we have drawn it wrongly, but on the other hand we can, this is a planar graph because we can draw it like this. We can draw it. So, this is our graph, right. We can draw it like yeah, it is possible to draw it like this, right. So, now no 2 edges are crossing each other, no 2 edges are intersecting with each other other than at the end points, right. So, for instance, so what about this one? This is a typical non-planar looking figure. So, in the sense that okay. So, some kind of a cube, right. So, structure, the edges of a cube is drawn here. So, is it possible to draw it on a plane? Is it a planar graph? See, now as we have drawn, it is not a plane graph because so the edges are crossing here, right. Several edges are crossing each other here, isn't it. So, this edge is crossing here, these 2 edges are crossing here. So, this is not a plane drawing, but then it can be drawn on the plane like this. So, what you do is this lower square can be drawn like this, right. Then now this upper square can be drawn like this, and then see these connections, these 4 connections will draw like this. So essentially this is same. So as if we have just projected it with a little, so this upper faces become like this, right. So that at one look some graphs may look non-planar, but they can be planar. So like this. So it will take some effort to figure out whether it has a drawing, or not. It has a drawing or not. For instance, you can ask whether this graph. So this is what. And then here this is a K5. So this is a K5. K5 means the complete graph on 5 nodes. Is it a planar graph? So you can try it out whether you can draw it on the plane, but after some effort you will see that it cannot be drawn on the plane. So for example, you can argue like this. So you take a triangle. So from K5 you take a triangle. So triangle anyway, however you draw, it will form a closed region, right. It may be like this, some triangle 1 2 3. Then the fourth node has to be either outside this triangle or inside this triangle. Say if it is outside also not a problem, inside also, because finally outside and inside you can, with some if you carefully look, you can see that it does not make much difference. So suppose it is inside, right. Then 4. So because these connections are there, so that it will divide the inner region into 3 triangles again. Where can 5 be now? If 5th node is outside, then how will I connect 4 and 5? So it will have to cross, right. So it has to be inside. So now if it is inside, you can see that it should be in one of these triangles. For instance, if it is 5 here, then this 5 is enclosed by this triangle. So this is outside. So if it is here, 5 is enclosed by 1 4 3 triangle, and then 2 is outside it. So similarly, if it is inside 1 2 4, then 3 is outside and 5 is inside. So every time you will have to cross the borders of a triangle if you are putting inside this. So therefore you can see that all the 5 vertices cannot be placed on the plane in such a way that the edges does not cross each other, right. So so this is probably the smallest in the number of vertices. This is the smallest graph on the with the smallest number of vertices which cannot be drawn on the plane, right. So there is another graph called K33 which cannot be drawn on the plane, which I leave it to you to figure out why it cannot be drawn on the plane. This has 9 edges. This is the smallest graph in the sense of number of edges which cannot be drawn on the plane. Now going back to, this is just an introduction to what kind of graphs are planar graphs. So my intention is not to give a very rigorous treatment of planar graphs. So I recommend to read the chapter from Reinhard Distel's graph theory textbook to get a very rigorous treatment of this subject, but to avoid the boring details, I would rather stick to some intuitive explanations about it. So first thing I want to consider is a famous theorem, famous formula regarding planar graphs. So it is called Euler's formula. So see in these cases, in these cases we have seen, so see this consider a plane graph. See, in a drawing like this kind of maximal connected regions, right. So this kind of regions are the faces. These are the faces of this thing, 1 2 3rd face, 4th face. So these are the faces of this thing. So for instance, if it is a tree, then there will be only one face, right. So this entire one face is connected. So see now the Euler, so again another example, here how many faces are there? Say for instance, one face, second face, third face, fourth face outside. This is one face, right? So now the Euler formula tries to connect the number of vertices, the number of edges and the number of faces in a planar graph. So it says n minus m plus l equal to 2, n minus m plus l equal to 2, where m is the number of edges, n is the number of vertices, l is the number of faces. For instance, if you take a tree in a connected planar graph, not in any planar graph. So, so here the number of faces l equal to 1, and here is number of vertices is n, then how many is the edges? N minus 1. So n minus 1 is 1 and another one is 2. So it's, so for instance you can take a cycle, say cycle, there are number of edges equal to n here. So there are n vertices and n edges. So n minus n plus l equal to 2 is what it says. What is 2? L. So l is the number of faces here. So one face, second face. So this is 2. So this cancels off. So here that is also correct. So this is what Euler formula says. We can try some other examples also. For instance, we can consider a wheel graph. So here it's essentially 1, 2, 3, 4, 5, 6, 7 faces here, right? 7 plus 1, 8 faces here, L equal to 8. Now how many edges are there? 1, 2, 3, 4, 5, 6, 7 edges. 1, 2, 3, 4, 5, 6, 7 edges here, and then similarly 7 edges there, right? 7 right. So we have 14 edges. So number of vertices is how much? The seven plus 1, 8 minus 14 plus 8, that is 16 minus 14 equal to 2 again. So I just did some to make you familiar with the parameters. I just did some examples. So now let's look at the proof of it. It's very easy in fact. So you can fix the n. So that way I am doing a very informal proof, not that I don't get into the details of topological details of why certain things faces are like this and all. So intuitively I will tell why it is. So suppose you consider n vertices, you fix n vertices. Now this you can do an induction on the number of edges. So for instance the connected graph, the minimum number of edges possible is n minus 1, right. So we have already seen it's a tree. So the number of faces is 1. So we have n minus 1 plus 1 equal to 2. So that's correct. Now for m edges it's true. Now if you consider on n vertices m edges, sorry m plus 1 edges, up to m edges we have verified. So now, so what do? We see that this you can because there are more than n minus 1 edges, there is a cycle. So you can remove one edge from such a cycle. So easily you can see that see when you remove one edge, the number of faces so increases. For instance, if this was the situation before, so if you remove one edge like this, so this regions, these two regions will combine and will become a bigger face, right. So that means the number of faces will decrease by 1, while we have added sorry, we have reduced the number of edges by 1. So in other words, so for instance compared to the earlier one, wherever this face we have, when you added this edge one, the number of faces increased by 1, and number of edges increase by. If you look at the formula, it is n minus m plus l, right. So, if this increases by 1 and this also increases by 1, they cancel off. So, the 2 earlier it was just 2, then it will remain 2. So, that is the induction on the number of edges and number of faces. So, because as you add, so suppose earlier you had this formula correct, n is fixed, for a smaller number of edges this is correct, and then you are adding one more edge. So, this will tend to go down, but then the number of faces increases to balance it, that is the only thing. So, therefore, the Euler formula is correct. Now, we will show that from the using the Euler formula, that the number of edges in a planar graph can at most be the number of edges in a planar graph, in a connected planar graph, is at most 3 n minus 6. So, okay, so here to do this thing, so let us say, so the number of the plane graph with n greater than or equal to 3 vertices, at most 3 n minus 6 edges, simple. So, this is so here what are we going to do? Here we can see that see the Euler formula tells us n minus m plus l equal to 2. Now, each, so we can always, we want to convert, we want to get rid of this L. Now, we know that every edge is part of, so for instance, if you want to get a how much is m. So, we can say that each face will contribute at least 3 edges. So, there should be at least 3L edges, 3L edges, right. We may tend to think like that, but then because the same edge, see for instance 2 faces may say that this face gives one edge here, but then this face gives the same edge here. So, we can tell this thing, right. So, number of edges has to be at least 3L by 2, right. So, right. So, we can m is greater than or equal to 3L by 2. So, what we do is initially right, we can add edges so that it becomes maximal, right. So, you can easily see that there is no so face which does not give right, it becomes triangulated, because if it is not triangulated, right, you can see that you can add every face is a triangle, you can see finally, right. If it is not a every face is not a triangle, then you could add one more edge, right. What we are going to do is fix a planar graph with, so let the number of vertices be n. Now, we will add edges to this planar graph in such a way that the number of edges is as big as possible, as much as possible. So, in other words, it becomes edge maximal with the property of planarity, right. So, it is very clear that every face has to become a triangle at this point. Why? Because if it is not a triangle, so you will see a face like this, right, somewhere. So, then you can always connect to such edges and put one more edge. It is possible to put one more edge without crossing, because it is inside the face. So, therefore, it becomes a triangulated graph, and therefore, essentially what we are telling is correct, is strict here. It is in fact each face will contribute 3 edges. So, it will be equal to 3L in that case. So, when it is triangulated and maximal. So, m is, I can say that m equal to 3L by. So, if I am considering only triangulated graphs, I can write m equal to 3L by 2, right. Now, So over L equal to 2m by 3, isn't it? Now I can substitute in the Euler formula n minus m plus L equal to 2, for with this L equal to 2m by 3, L equal to 2m by 3. So what happens? N minus m plus 2m by 3 equal to 2 is what it says. Now this is essentially n minus cm by 3, right, equal to 2. Now multiplying by 3, so we get 3n minus m equal to 6. So we get m equal to 3n minus 6, and this is the case of the maximal planar graphs. So essentially when I cannot add any more edge to the planar graph without losing planarity. So at that case this is equal to 3n minus 6. That means any planar graph which is not maximal will have strictly less than 3n minus 6, less than equal to. So we cannot ever make a planar graph more than 3n minus 6, the number of edges more than 3n minus 6. So we will in the next class we will see how this observation can be used to get a 6 coloring of planar graphs, vertex coloring using 6 colors. Thank you.